Hey everyone, I'm Priyanshu Pandey. Today, we're diving into a story about, well, a great escape, an impossible escape, actually. And it's happening constantly, right in the heart of the atom. And this really is the central mystery we're talking about today. I want you to picture something, a particle, trapped inside this unbreakable fortress. The walls are so high, so strong, that all the known laws of physics say escape is impossible. It should be in there forever. But it gets out. All right, so let's get into what this prison actually is. We're talking about the atomic nucleus. This is one of the densest, most tightly packed places in the entire universe. It really is a fortress, and it's held together by a force that is just mind-bogglingly powerful.
That force is the strong nuclear force. You can think of it as the warden of our nuclear prison. I mean, this thing is 100 times stronger than electromagnetism. It acts like this cosmic superglue, just yanking all the protons and neutrons inward and clamping them together. Nothing should be able to fight it.
But inside this fortress, there's a constant battle going on. You've got the strong force pulling everything in, right? But at the same time, another force, the Coulomb force, is trying to blow the whole thing apart. See, all those protons are positively charged, so they're desperately trying to push away from each other. It is a non-stop, epic tug of war.
So here's the bottom line. According to the physics everyone knew at the time, what we call classical physics, for any particle to escape, it would need a massive, absolutely colossal amount of energy to get over that wall created by the strong force. The problem? The particles inside just don't have that kind of juice. So the verdict was clear. Escape is impossible. The prison is perfect.
And yet, it happens. We see it happening all the time. These heavy, unstable nuclei, they just spit out particles. We call this alpha decay. Now, you can imagine this was a huge puzzle for physicists back in the early 20th century. Their rulebook, everything they thought they knew, said one thing, but reality, what they were actually observing, was showing them something completely different.
Which brings us right back to that big question. If the inmates can't climb over the wall, how in the world are they getting out? The evidence was right there, you couldn't deny it. But the only way it could be happening seemed to break the fundamental laws of nature.
And when scientists looked at the data, the mystery just got deeper. I mean, check this out. Polonium-212 spits out an alpha particle that's only about twice as energetic as the one from uranium-238. So you'd think, okay, maybe its half-life is a little shorter, right? Nope, it's shorter by a factor of 10 with 25 zeros after it. That is just an insane difference. This bizarre relationship was totally inexplicable. A tiny, tiny tweak in energy was causing this astronomical, unbelievable change in how stable the nucleus was. The old classical physics model wasn't just a little bit off. It was spectacularly, fundamentally wrong. It had no answer for this. None.
So the answer wasn't about tweaking the old rules. It came from throwing out the old rulebook entirely and starting with a new one, a completely new one, called quantum mechanics. And this totally new way of looking at the universe, well, it offered a solution that was both bizarre and absolutely brilliant.
This really gets at the heart of the new thinking. In the old classical view, a particle is like a solid little ball, a marble. If you don't push that marble hard enough, there's no way it's getting over a hill. End of story. But in the quantum world, a particle isn't really a solid thing at all. It's more like a wave of probability. And here's the kicker, that wave can leak.
This is the incredible phenomenon known as quantum tunneling. The particle doesn't need the energy to climb over the wall. Instead, there's this tiny but not zero chance that it can just, poof, appear on the other side. It's literally like a ghost walking right through a solid brick wall. It doesn't break the wall, it just tunnels through.
Now, this escape isn't a sure thing, not at all. It's a pure game of chance. You can imagine that alpha particle inside the nucleus, just bouncing around, hitting the walls trillions of times a second. It's like a prisoner rattling the bars of the cell over and over and over, just waiting for that one in a gazillion lucky break to tunnel out.
And then in 1928, a physicist named George Gamow actually figured out how to calculate the odds of that lucky break. He came up with a formula, we call it the Gamow factor now, that could predict the exact probability of this tunneling event. And this was a huge moment. It was one of the first big wins for quantum theory, proving that these weird new rules could actually explain things we see in the real world.
And here's the absolute key to the whole puzzle. Gamow's formula showed that the probability of tunneling is extremely sensitive to the particle's energy. I'm talking exponentially sensitive. What that means is that even a tiny, minuscule change in the particle's energy has a gigantic, outsized effect on its chances of escaping.
And that is what explains those wild numbers we saw earlier. A small drop in energy makes the probability of escape just plummet. It goes from being pretty likely to almost impossible. And that's why the half-life, the time it takes for half the stuff to decay, just skyrockets from microseconds to billions of years. Suddenly, it all made sense. The mystery was solved.
But Gamow's theory wasn't the final chapter. It was the foundation, the blueprint. For nearly 100 years now, scientists have been building on that blueprint, refining our understanding, and getting better and better at predicting how nuclei will behave.
So you can see the whole journey here. We went from just observing a pattern, the Geiger-Newton law, to Gamow giving us the why with his quantum theory. Then fast forward to the 2000s, and scientists are creating even more precise formulas. And now we're feeding all of that historical data into machine learning models, using AI to make predictions that are more accurate than ever before.
But you know what's really amazing? Even today's most sophisticated AI models are, when you get right down to it, still working from the same fundamental truth that George Gamow figured out almost a century ago. That the universe doesn't play by our common sense rules. It plays by the weird, spooky rules of quantum probability.
So, this whole story of the great quantum escape leaves us with a pretty wild thought, doesn't it? It teaches us that in the quantum world, impossible is, well, it's often just a different way of saying really, really, really improbable. And that just makes you wonder, right? What other unbreakable walls in our universe are just a matter of probability? What other great escapes are just waiting to happen?